In Episode 1, the wizard built a grid for you and combat ran. In this episode, we slow down and look at that grid system in detail. By the end, you will know what every object in the grid hierarchy does, what properties a cell exposes, and why. How grid objects, including actors, are registered and tracked, and how the system figures out where the mouse cursor is pointing on the battlefield. This knowledge pays off in every subsequent episode because pathfinding, movement, attacks, and targeting all work through this layer. Start by expanding GridManager in the hierarchy. You will see 4 important children. First, cells. This is where every individual grid tile lives as a child game object. The wizard generated all of them for you. Second, objects. Any actor or obstacle that exists on the grid at scene load time should be parented here. We will come back to that. Third, mask. This is the cursor footprint that follows the mouse across the battlefield. It is what highlights cells under the pointer during player actions. Fourth, wireframe tile map. This is purely visual, the checkerboard underlay you see in the scene. With GridManager selected, look at the inspector. The top section references the 4 child components: grid, grid mask, cell highlighter, and objects list. These are the pieces the manager coordinates. Below that, you will find the directional settings. We will cover those when we reach the movement direction section. One thing worth knowing now is that GridManager is the single entry point the rest of the toolkit uses to ask grid questions. Find a cell at these coordinates. Find what is under the mouse. Get all neighbors of this cell. Nothing talks to cells or grid objects directly without going through GridManager. Let's look at the grid component itself. Select the grid child object. The 2 most important fields here are width and height. These are the dimensions set by the wizard, and they define how many columns and rows the battlefield has. These are read at initialization and cannot be changed at runtime. Below them, you will see Show Grid Wireframe and Wireframe Alpha. If I turn off Show Grid Wireframe, the checkerboard underlay disappears. The gameplay grid still exists. All cells are still there. Pathfinding still works. Because the wireframe is purely visual. The actual logic lives on the cells. Turn it back on and bring Wireframe Alpha down to about 0.10. This is a common adjustment when the wireframe makes the scene feel too technical or distracts from the art. Now let's look at cells. Expand the cell's child object. Each child game object here is a single grid cell. Click any one of them. In the inspector, you will see the cell's coordinate field. This is a vector 2 that gives its column and row position on the grid, starting from 0 at the bottom left. This coordinate is the cell's permanent identity. Below the coordinate is active. An inactive cell is completely disconnected from the grid. It does not participate in pathfinding, it cannot be targeted, and it does not receive the hovered cell highlight. This is how you carve non-rectangular battlefields. You define a rectangular grid at wizard time, and then deactivate the cells that should not be part of it. Cliff edges, walls, out-of-bounds areas. Toggling one cell at a time in the inspector works for spot fixes. But for shaping an entire map, you would be clicking through dozens of cells. The toolkit gives you a much faster way, which we will look at right now. Select the GridManager object and look at the scene view. There is a toolbar overlay labeled TBCS Grid Editor. It contains 4 icon buttons. These are edit mode painting tools that let you modify cell data directly by clicking in the viewport instead of selecting cells one by one. They work in both edit mode and play mode. The first button is Toggle Active Cell. Click it to enter paint mode. The button highlights to show it is active. Now click any cell in the scene view, and it immediately toggles its is active state. Click it again to restore it. You can paint across multiple cells in sequence without leaving the scene view. Every change is registered as a separate undo step, so you can step back through them with Ctrl+Z if you overshoot. When you are done shaping the boundary, click the button again to exit paint mode. The second button is Toggle Line of Sight Blocker. It works the same way. Click the button to enter paint mode, Then click cells in the viewport to toggle their BlocksLOS state.
We will cover what BlocksLOS means in a moment. The important thing to see here is the visual feedback. While this tool is active, every cell with BlocksLOS set to true shows a cyan ball gizmo in the scene view.
This makes it easy to see the full vision blocking layout at a glance without inspecting each cell individually. Click the button again to exit paint mode and hide the gizmos. The third button is Fit Cells to Terrain. This is an experimental tool for 3D scenes. When you click it, the system raycasts against any Unity terrain in the scene and automatically deactivates cells that fall outside the terrain's playable surface, useful for maps with uneven or island-shaped ground. It has no effect in 2D scenes. The fourth button is Clear All. Clicking it resets every cell in the grid to active with no LOS blocking. A clean slate if you want to start your map shape from scratch. Now let us look at the two cell properties those tools modify and understand what they actually mean at runtime. MoveCost is an integer that represents how expensive it is to enter this cell. The default is 1. A cell representing a swamp or rough terrain might have a move cost of 2 or 3. Pathfinding multiplies this value by the direction cost when calculating routes, so higher cost cells are avoided when cheaper routes exist. You set this per cell in the inspector. There is no paint tool for move cost because terrain cost is usually tied to a specific art asset or trigger zone rather than something you brush freehand.
Block's line of sight is a Boolean that marks the cell itself as a vision obstacle, independently of any objects on it.
This is especially useful for static scenery objects that would spawn across multiple cells in irregular shape and cannot be considered grid objects.
As we just saw, the toggle line of sight blocker tool in the scene view toolbar is the practical way to set this across many cells at once.
You will also see a clearance field on each cell. This is a read-only value calculated at runtime by the GridManager when a size 2 actor is selected. A clearance of 1 means a 1-1-1 actor can stand here. A clearance of 2 means a 2-on-2 actor also fits. GridManager recomputes clearances automatically whenever the selected object changes, so this value is always current. You never set it manually. It is derived from the surrounding cell layout. Each cell has a visual overlay layer driven by the TBCS cell overlay component. There are 3 overlay types: walkable, attackable, and targetable. These are the colored highlights you see on the battlefield when you select an actor or preview an attack. The system marks and unmarks these overlays through the GridManager's cell highlighter using a bitmasking algorithm. The cell highlighter checks each highlighted cell against its 8 neighbors and selects a matching sprite from a set of 47 border variants. This is what gives the range previews their smooth, connected edges instead of individual squares. The cell overlay also has an alpha field. This controls the transparency of all 3 overlay types at once. If the walkable and attackable highlights feel too strong for your game's visual style, this is where you reduce them. A value between 0.5 and 0.7 is a typical starting point. Now let's look at how things that exist on the grid are represented. Look at the objects container. Actors manually placed and those spawned via the spawner at runtime will be here. For convenience in this episode, I've put a prop object to serve as an example. Every object here has a grid object component, or an actor component if it's a living entity. Our barrel prop, being an inanimate object, has a grid object component, which is a simpler version of the actor component. The 2 most important fields here are blocks movement and blocks vision. Blocks movement makes this object a pathfinding obstacle. No other actor can move through or end their turn on a cell occupied by a blocking object. Blocks vision makes this object block line of sight checks.
An actor has blocks movement set to true by default.
A transparent magical barrier might have blocks movement false, but blocks vision false too. A solid crate might have both true. Grid objects also have a size field. Size 1 means the object occupies a single 1x1 cell. Size 2 means it occupies a 2x2 block of 4 cells. GridManager reads this at initialization and marks all 4 occupied cells accordingly. This is the same size you set in the new actor wizard when building a large character or vehicle. The GridMask child object hosts the GridMask component. Its job is to track which cells are currently under the mouse cursor, but it's mostly useful for size 2 actors to allow for finer grid movement. The most relevant field here is actor size. When you select an actor, the system sets the mask size to match that actor's size value. A size 1 actor produces a single cell hover indicator. A size 2 actor produces a 2x2 hover preview, which is especially useful when placing or moving large units, so you can see exactly where the full footprint would land. There is also a Show Mask debug toggle. Turn this on at runtime and you will see a gizmo in the scene view that tracks the mask position. This is useful when diagnosing cursor issues. If the hover highlight appears offset from where you expect it, Show Mask lets you see exactly where the system thinks the cursor is pointing. Back on GridManager, look at the 2 direction fields, Cell Connections and All Directions. Both are Grid Directions assets, scriptable objects that define a list of directional steps and their movement cost multipliers. Cell Connections is used by pathfinding. It determines which neighbors a cell can reach during movement. The default 3D configuration uses 8 orthogonal directions. If you want 4-way cardinal movement, you would swap this for a directions asset that only includes the 4 cardinal steps. All directions is used for things that need to check all 8 surrounding cells regardless of movement rules. Line of sight, reaction ranges, area effect targeting. It always covers all 8 neighbors.
Defining the directions as swappable scriptable objects allows for maximum flexibility in case you want to change the rules of movement or even the shape of the cells.
Click through to the Cell Connections asset.
Each entry in the list has a step, a vector 2 offset like 1, 0 for east, and a cost multiplier.
For orthogonal steps, the multiplier is 1. For diagonal steps, you would typically use 1 as well, or a higher value if you want diagonals to cost more than orthogonal moves. The pathfinding system multiplies the cell's move cost by this multiplier when evaluating that neighbor. If your game needs an unusual movement topology, hexagonal style movement for example, you configure it here by choosing the right set of step vectors. When you need to place an actor or obstacle at edit time rather than via the spawner, the correct workflow is: parent it under GridManager inside the object's container. Position it roughly over the desired cell in the scene view, then go to TBCS Grid. Snap Objects to Grid. Snap Objects to Grid finds the nearest valid cell for each grid object and actor found under the object's container and registers it at the data level. Transform position alone is not enough. The cell's occupied objects list and the object or actor's coordinate reference are only updated by the snap step, not by moving the transform. After the snap, if you select the cell the actor now occupies, you will see it listed in the cell's Objects on Cell list. That is the live data registration. If that list is empty after a manual placement, the snap did not happen, or the object or actor is not inside the object's container. As a reminder, for anything more than 1 or 2 actors, the cleaner approach is still the spawner, which handles placement and registration automatically at scene startup. Manual placement is still possible for actors, but it's better to keep it for static prop objects. Here is what you now understand. GridManager coordinates the whole battlefield. The grid holds dimensions in the wireframe. Cells carry the gameplay data, coordinate, active state, movement cost, vision blocking, and clearance. The Scene View toolbar gives you paint tools to shape those states directly across many cells at once, with full undo support.
Grid objects track what lives on each cell and whether it blocks movement or vision.
The cell overlays give players visual feedback on ranges and targets. The grid mask tracks cursor position, and the movement directions assets control which neighbors are reachable and at what cost. In the next episode, we build a complete actor from scratch, walking through every component in the stack, understanding why each one exists, and getting it into the turn order for the first time.